Process technology. Unit 15. Digital transformation of the process industry. Outline. What is digital transformation? Digital technologies. The benefits of digital transformation. What is digital transformation? Digital transformation of the process industry refers to the integration of digital technologies and business model changes to fundamentally improve operations, business processes, and customer experiences. The application of digital technology has a long tradition in the process industry. Process control systems and sensors have been used in production for decades. So, the industry is not starting digital transformation from zero, although certain factors differentiate the current period. Digital technologies. Internet of Things. Big data analytics and artificial intelligence. Cloud computing. Automation and robotics. Digital twins and mathematical modeling. Virtual reality and augmented reality. Blockchain and smart contracts. Digital technologies. Internet of Things. The Internet of Things, IoT, is a set of sensors connected with a digital platform which are used to collect, transfer, and analyze raw data in real time to get a clear picture of processes at the facilities, improve operational efficiency, reduce energy consumption, and drive profitability. Sensors are being embedded in equipment and assets to monitor parameters and enable real-time tracking. Wireless sensors deployed across the equipment detect leaks, monitor asset health and identify anomalies. The sensors generate data that provides insights into equipment performance, energy usage and production levels. IoT enables remote monitoring and control of assets. By monitoring equipment data in real time, the companies can optimize production, minimize downtime and predict maintenance needs. Benefits of IoT. Real-time visibility. IoT provides real-time view into equipment performance, safety and environmental conditions, enabling the companies to continuously monitor their facilities. Predictive maintenance. The data from sensors installed at processing facilities enables predictive analytics and root cause analysis. They help identify pre-failure conditions and perform maintenance in advance to avoid major downtimes and ensure smooth operation and smarter utilization of assets. Hazard management. IoT solutions monitor the presence of flammable gases and toxic vapors in the atmosphere and help prevent gas leakages or liquid spills. Accident prevention capabilities of IoT also make operations safer and reduce injury rates by enabling advanced workplace safety monitoring and instant danger alerts. Reduced environmental impact. process industry is one of the largest contributors to climate change via greenhouse gas emissions. To reduce the environmental impact, the operators can reduce fugitive emissions and flaring with the help of IoT-enabled leak detection and predictive maintenance. Autonomous work of machines. IoT enables machines to complete tedious tasks without human intervention. As a result, human resources may be transferred to more complex tasks that require personal skills, especially out-of-the-box thinking. Companies can automate processes, reduce labor costs and cut down on waste. Increased overall profits. The IoT solutions contribute to the cost efficiency. By optimizing the use of the facilities, equipment, resources, and workforce, the IoT solutions provide the companies increased productivity and reduced expenditures, thus increasing the overall profits. Big data analytics and artificial intelligence. The vast amount of data generated by IoT devices and other sources has promoted the adoption of big data analytics and artificial intelligence technologies in the process industry. Artificial intelligence and machine learning algorithms are used to gain actionable insights from petabytes of data related to equipment performance, asset health, energy usage, etc. Artificial intelligence is also used for applications like autonomous drones for inspection, virtual assistants, and cybersecurity threat detection. Advanced analytics helps optimize operations, improve efficiency, predict equipment failures, detect anomalies. Cloud computing. Cloud computing plays an important role in enabling digital transformation in the process industry. The cloud provides scalable infrastructure for storage, processing, and analytics of data related to IoT sensor data, production data, etc. It allows sharing of data and insights across the value chain. Cloud computing gives the companies flexibility, agility, and the ability to harness massive amounts of data for insights, thus allowing the companies to improve efficiency, to maximize uptime, to enhance sustainability. Automation and robotics. Automation and robotics are increasingly being adopted in the process industry to improve efficiency, safety, and productivity. Automated systems handle repetitive and hazardous tasks like valve monitoring and control, pipeline pigging, and tank gauging. Robotic systems perform functions like inspection of pipelines and equipment, maintenance of difficult-to-reach areas, and material handling. Automation and robotics. Reduce manpower requirements. Improve accuracy. Minimize human error. Free up workers for higher value tasks. Digital twins and mathematical modeling. Digital twins are virtual models of physical assets that provide a real-time 3D representation of an asset. Digital twins allow simulating and optimizing different aspects of operations, from production to pipeline management. Digital twins have many applications in the process industry. Facility lifecycle management. Design and construction. Before building new facilities, digital twins can simulate their design to ensure they meet all requirements and identify potential improvements. Decommissioning. As facilities reach the end of their life, digital twins can aid in planning their safe and efficient decommissioning. Asset performance management. Predictive maintenance. Using sensors and real-time data, digital twins can predict when equipment might fail. This helps companies fix problems before they happen, reducing downtime. Operational optimization. Digital twins can model the entire operation of an asset. By simulating different conditions, companies can find the most efficient way to run their operations. Simulation of asset operation. Flow simulation. Digital twins model the flow through pipelines and other infrastructure. This can help identify bottlenecks or inefficiencies in the system. Yield maximization. Companies can simulate different conditions, like temperature or pressure, to find the optimal settings for maximum production. Health, safety, and environment. Safety training. Digital twins can recreate emergency scenarios, for example, a fire, in a virtual environment. This allows workers to practice their response in a safe, controlled setting. Environmental monitoring. Digital twins can monitor emissions, wastewater, etc., in real time, ensuring companies meet regulatory standards and reduce their environmental impact. Supply chain and logistics. Inventory management. Digital twins can track the storage, usage, and replenishment of parts or chemicals, optimizing inventory levels. Optimization of transportation. By modeling the transportation of flows, digital twins can find the most efficient routes and methods. Real-time monitoring and control. Remote operations. Digital twins are particularly useful in offshore or remote sites. They allow operators in centralized control rooms to monitor and control equipment from a distance. System performance. By continuously comparing the digital twin's performance with the real-world asset, discrepancies can be spotted immediately, leading to quick interventions. Digital twin of a centrifugal pump. Functions of the digital twin. Duplication of the data from physical sensors to virtual sensors. Analytical calculation of the hydraulic characteristics of the pump based on the data of the mathematical model. Calculation of indicators of energy efficiency of the pump. Predicting the residual life of critical pump and motor parts based on regression methods to predict failures by the direct measurements of equipment operation parameters. Economic effect. The economic effect from the introduction of a digital twin, providing the intelligent, smart, and continuous diagnostics of the technical condition and regulation of the operating mode of the pump, consists of direct and indirect savings. Direct savings. Reduction of repair costs and increase in the time between repairs due to the reduction of unreasonable planned repairs and unplanned repairs due to failures. Reduction of energy costs, by regulating the operating mode of the pump based on the calculation of energy efficiency indicators. Indirect savings. Reduction of losses resulting from unplanned downtime, for example, losses in the form of unearned income for the product shipment, lost profit. Reduction of the costs resulting from eliminating of accidents that may arise due to equipment failures, and improving production safety. Mathematical modeling is used because mathematical modeling is more economical than physical modeling and experimental research. Mathematical modeling is safer than physical modeling and experimental research. In other words, conducting a computational experiment using a mathematical model requires less material and time costs compared to physical modeling. In addition, when using mathematical models, the impact on the environment, health and safety of personnel is minimal. The main task of mathematical modeling is to create a digital image of the object being studied, that is to obtain a mathematical description of an object in the form of mathematical expressions. This is necessary not only to imagine and study the object, but also to predict its behavior when the initial parameters change, and as a result, control the object. There are 5 levels of mathematical modeling. The molecular level, at which the physical and chemical interactions of individual molecules are considered. The small volume level, which is an ensemble of molecules located in an infinitely small volume of the reaction space, considered as a single whole. The level of the working area of the apparatus, the object of study of which is individual areas of the working space of the apparatus. The level of the apparatus, at which the operation of the apparatus as a whole is modeled. The level of the system, modeling of the interconnected operation of several devices. The molecular level. In oil refining, Level 1 of modeling is aimed to determine the composition of oil and oil fractions, as well as their physical and chemical properties. This type of modeling is carried out in special software packages. They contain databases that include fairly complete information about the composition and properties of almost all oils from all fields in the world. The small volume level. At the small volume level, all processes occurring in devices are considered from the point of view of individual elements of the medium. The figure represents the elementary volume of liquid. Taking into account the action of all forces on an elementary volume of liquid allows deriving the system of fundamental Navier-Stokes equations. The left sides of the equations describe inertial forces arising in a moving fluid. The right sides of the equations describe gravity forces and frictional forces. These equations are used to describe hydrodynamics, the movement of a fluid, in various processes. There are also similar differential equations for describing thermal and mass transfer processes. By integrating such systems, it is possible to obtain a complete mathematical description of all the phenomena under consideration. However, in most cases, solving such equations analytically is not possible. Such problems can be solved using large computing power and various methods of computational mathematics implemented in specialized software packages, for example, ANSYS Fluent, OpenFOAM, etc. The initial data for modeling in this case are the properties of the media being studied, as well as the surface geometry and material characteristics. The result of the simulation is data on changes in the studied parameters at all points of the system. The use of programs allows obtaining a visual picture in the form of a video or static image. The figure shows modeling of the process of fluid flow through a valve. The level of the working area of the apparatus. Software packages for modeling also allow calculating of the processes for the working areas of the device, but this requires large computing power. The level of the apparatus. Modeling of individual devices combines all the processes occurring in the device and its constituent working areas into a mathematical model. The figure illustrates the modeling of pressure distribution during operation of a centrifugal pump. The result of such modeling is the generation of material and thermal balances of the device, determination of the optimal modes of its operation, and determination of its main characteristics. The level of the system. Modeling at the level of the system combines models of individual devices into the process units. For this, software systems such as ChemCAD, Aspen HiSys, DWSim and others are used. They allow building of engineering models from a standard set of equipment. The figure presents the modeling of diesel fraction separation unit in Aspen HiSys package. Such models provide calculation of the characteristics of process flows and the required equipment parameters, selection of optimal operating modes for the entire unit as a whole system, Prediction of the behavior of the unit when its operating conditions change. Carrying out of the intelligent control of the process. There are also more global models that cover the entire production as a whole. They are the so-called LP models. They are built on the principles of linear programming, and, in fact, represent a set of tables of material balances, consumption rates of raw materials, reagents and energy resources of technological units. These models also take into account restrictions from the suppliers of raw materials and the consumers of products. The aim of such models is to combine all available data into a single matrix and carry out calculation of this matrix in order to find such operating conditions for the enterprise as a whole, under which not only the maximum yield of products, but, first of all, the maximum profit is achieved. LP models solve economic problems, and they provide calculation of profits taking into account costs and restrictions from the suppliers and consumers. Determination of the optimal set of products for manufacturing. Economical evaluation of the impact of unit operating modes on the entire production. Creation of the business plan for production. Virtual reality and augmented reality. One of the main applications of VR and AR in the process industry is staff training. The process industry always needs the experienced workers. However, training workers on site is an expensive and dangerous process. This problem can be solved using the VR technology. VR headsets can provide workers with practical training without the need to visit the plants. Predictive maintenance is another application of VR and AR tools. AR headsets can significantly improve maintenance efficiency by providing graphical information and step-by-step instructions. Blockchain and smart contracts. Blockchain and smart contracts hold significant potential to transform transactions, asset tracking, and supply chain management in the process industry. Blockchain can improve transparency, traceability, and data sharing across the complex supply chain involving multiple stakeholders. Smart contracts are self-executing contracts enabled by blockchain. They automate payments, document exchanges, and other transactions. The industry uses blockchain and smart contracts for applications like trading energy commodities, tracking crude oil from wellhead to refinery, digitizing contracts, and managing financial settlements and royalty payments. Digital technologies. Internet of Things. Big data analytics and artificial intelligence. Cloud computing. Automation and robotics. Digital twins and mathematical modeling. Virtual reality and augmented reality. Blockchain and smart contracts. The benefits of digital transformation. Digital transformation powered by digital technologies has the potential to revolutionize every aspect of the process industry. By leveraging data insights, optimizing and streamlining processes, digital technologies can help companies improve efficiency, enhance safety and sustainability, reduce costs, increase overall profit. Revision. Explain what is digital transformation. What digital technologies are used in the process industry? Explain what is the Internet of Things. List the applications and benefits of the Internet of Things. What algorithms are used for big data analytics? List the applications and benefits of the advanced analytics. List the applications and benefits of the cloud technologies. What are the functions of automation and robotics? What benefits do automation and robotics provide? Explain what is a digital twin. List the applications and benefits of digital twins. What are the advantages of the mathematical modeling over the physical modeling? Explain what is a mathematical model. Specify the levels of the mathematical modeling. What functions do software packages for modeling provide? List the advantages of using the software packages for modeling. List the disadvantages of using the software packages for modeling. Explain what are LP models. What problems do LP models solve? List the applications and benefits of virtual reality and augmented reality. List the applications and benefits of the blockchain technology and smart contracts. What are the benefits of digital transformation?